So question 1 is saying, which branch of chemistry would a grade 12 learner intending to become a pharmacist study? Which branch of chemistry would a grade 12 learner intending to become a pharmacist study? So you have the branches of chemistry. So in chemistry, we have certain branches like analytical chemistry, biochemistry, organic chemistry, physical chemistry, and we have also some other types like inorganic chemistry. So on top of these are called the branches of chemistry. If you're studying chemistry, these are the branches that you are going to look at. But in addition to that, we also have what we call inorganic chemistry. So inorganic chemistry is the opposite of organic chemistry. So we'll see what that means. And basically, these are the branches of chemistry that we have. So this grade 12 learner is intending to become a pharmacist. Now, you know what pharmacy is all about. Pharmacy actually studies how drugs work inside the human body. That is pharmacy. If we give this drug to this patient, how is it going to work in the body to cure the disease? That is pharmacy. So when you are looking at the branches here, notice that we have analytical chemistry. Now, analytical chemistry is simply about analyzing or measuring quantities of substances. That's all it is. Like, for example, if you are using titration, you are just trying to measure how much is this, and if we use this amount, what is going to happen. This branch is also part of pharmacy to some extent, but it's not really something that a grade 12 learner would intend to learn in order to become a pharmacist. It is part of pharmacy. Pharmacists usually learn analytical chemistry because you want to make sure that the drugs that you are giving to a person are actually in accurate amount. You don't want to give them too much or too little. So that requires some analysis, and that is what analytical chemistry is about. But it's not really a key branch of chemistry that this grade 12 learner is gonna intend to actually learn in order to become a pharmacist. So this one we can eliminate. When you look at biochemistry is bio, which means life, and then you have chemistry. So chemistry, we are talking about chemical processes. So this means this is the chemistry about life, and this life is pointing to the human body. In other words, when you look at the human body, the chemical processes that take place in the human body is what we call biochemistry. So biochemistry is more broad and deep, and it is more related to someone who is intending to become a pharmacist, because it is now analyzing how the human body works and how, when the drug is actually given to a patient, the processes it is going to go through from after it is ingested, then absorbed, and then it is going to be extended to the different parts where it is required to be used, and then how those parts are going to utilize that. That is biochemistry. So unlike analytical chemistry, which is just dealing with knowing how much are you going to have, biochemistry is going in more depth to understand how that drug is going to be absorbed and then transported to different parts of the body, and how those bodies are going to, or body parts are going to absorb or utilize that particular drug. So as far as pharmacy, you will realize that biochemistry is the branch of chemistry which a grade 12 learner would intend to learn in order to become a pharmacist, because this is encompassing many things, because it deals with the human body, the human body itself, and then when the drug is administered, you're going to study also the processes through which it is going to go. That is essentially what pharmacy is all about. So answer choice B is the correct answer for this particular one. When you're talking about organic chemistry, which is option C, organic chemistry is about organic compounds. you are simply studying organic compounds. So it's not really something that is going to be a key thing when it comes to pharmacy. You understand that drugs contain some organic compounds. That's why you are studying organic chemistry. But at the very foundation of pharmacy, it is biochemistry. Organic chemistry is also important, but it is not the key branch that you are going to use for a person like a grade 12 learner who is intending to become a pharmacist. So we can also eliminate this particular choice. So this is not the answer. And physical chemistry simply studies like the chemical processes, for example, the chemical rates and the energy utilization in the body, thermodynamics, the chemical equilibrium. So it also plays an important role for someone who is studying pharmacy, but it falls short when it is compared to biochemistry, because biochemistry in fact encompasses also some ideas on physical chemistry. So we can also eliminate this answer choice. So when you're talking about organic chemistry, you are talking about studying organic compounds. When you're talking about organic compounds, we'll look at some questions on organic chemistry. You have compounds that have carbon, they have oxygen, they have hydrogen, they have nitrogen, they have sulfur, and so on. So these are some of the components of organic compounds. They should have these elements, which means if you are talking about the other branch of chemistry, which is inorganic chemistry, when you look at inorganic chemistry, this is the opposite of organic chemistry, which means that you are dealing with non-organic compounds. So if you are dealing with, for example, sodium is not an element that forms organic compounds. So when you're studying sodium or aluminium or some other non-organic elements, then you are essentially studying inorganic compounds or inorganic chemistry. So when we are studying, for example, the particulate nature of matter, the elements, and on the elements we are studying sodium, calcium, what we are studying is inorganic chemistry. But when we are studying compounds that contain carbon, hydrogen, and oxygen, and sulfur, and nitrogen, then we are essentially studying organic chemistry. So make sure you understand the differences here. So that's what we can say on the first question. You have to understand the branches of chemistry, how you can distinguish between them. And if you have a question like that, where you have to identify which branch of chemistry would a grade 12 learner intending to become a pharmacist study, then you'll be able to know that, okay, I think the key here is biochemistry. So your exam might not come like this, where it is the same exact question, but the principles might be expressed in the question that you might have in your exams. So it might be dealing with the same branches of chemistry. So make sure you understand all those branches. All right. So having said that, we can go to the next question. If you have any questions, please, you can just open your mic and then ask, because I'm not able to read. If you try to type in the chat box, I might not see what you are asking for. So you can just open your mic and then ask. So let's go to the next question. Now, the next question is saying, which of the following shows the correct basic unit of matter contained in the stated substances? Which of the following shows the correct basic unit of matter contained in the stated substances? So we are talking about the basic unit of matter. That's the key. What does that mean? Well, the first thing that we need to understand is when you're talking about matter, matter is anything that has mass and also occupies space. So two things: it has mass and also occupies some space. So for example, when you take a rock, you look at the rock, that rock has got mass, because you can measure the mass of that particular rock. Not only that, because it is a substance, it does occupy some space. In other words, when you see it there where it is, it is actually occupying some space. There's some space which it is occupying. So when you're talking about matter, you are talking essentially about the physical substances. Because when you're talking about physical substances, these are substances that you can touch or feel. The fact that you can touch them shows that these are occupying some space, and also you can measure their mass. So anything that has mass and also can occupy some space is actually what we call matter. Now, when you're talking about matter, matter is made up of particles. So these particles of matter are, number one, atoms. Number two, molecules. And number three, ions. So basically, these three particles are the ones that make up matter: atoms, molecules, ions. But the next question is, if you understand that these are the particles that make up matter, what are atoms, what are molecules, and what are ions? So that's something that we need to discover. So how do we distinguish between these three particles? Now, when you're talking about atoms, an atom is understood to be the smallest particle of an element which can take part in a chemical reaction. That is how we understand an atom to be. Now, an atom is said to be the smallest particle of an element, which means that if you compare an atom with an element, because that is also another important particle that you can talk about, an element. If you say an atom is the smallest particle of this particular element, then you understand that the element is actually much bigger than the atom, because the atom is the smallest particle of this particular element. That's what we call an atom. Now, the example that we can give when we are trying to understand the difference between atoms and elements, because atoms are smallest particles of an element, which means an element is much bigger than an atom. For example, if we say blacks, we are blacks. We also have some people who are whites or who are red. Now, when you are talking about blacks, Africans, this is the category. In other words, when you mention the name blacks, you are talking about the race that is made up of only one type of persons, and that is black people. That's what you're actually saying. But you can actually look at the smallest particle of this race, which is an individual, the black person. The black person is going to be the smallest description or the smallest particle of this entire African race. So when you compare one single individual, a black person, you compare that individual with the entire race of Africans, you see that this entire race is actually much bigger than one individual. But we understand that this entire race is made up of only one type of people, that is blacks. So we are being defined by black. So this is what is happening when you're talking about elements. Elements are pure substances that are made up of only one type of an atom. Just like Africanism is a race that is made up of only one type of color, which is black. I hope you can get that concept. So an element is something much bigger because it is something that is made up of only one type of an atom. So in other words, you have an element, and within an element you just have only one type of an atom. For example, oxygen is an element. So, which means that within this element, you only have oxygen atoms. You only have oxygen atoms. In this particular element, you can't have hydrogen. You can't have carbon, because these are not the one type of an atom, part of an element. So you can exclude them. But these can exist on their own as elements. For example, this is an element of hydrogen, which means it contains only hydrogen atoms. Atoms are the smallest particles of an element. The same is true for carbon. You have carbon, but within carbon, it is made up of only carbon atoms. So these are elements, but they are made up of only the similar or the same type of an atom. So the smallest particle of any element is what we call an atom. Now, when you look at, I think the best example we'll be using is oxygen. I think oxygen is quite common. So this is oxygen. This is the symbol for oxygen. Now, I want you to understand that this oxygen can be written as an atom. But before we do that, you have to understand one thing, because after we've explained this, it will be easier for you to answer this question and also some other related questions on the topic, especially on the basic units of matter. When you are talking about an atom contains particles. It contains what we call protons. It contains what we call electrons, and it also contains what we call neutrons. Three key parts of an atom: protons, electrons, neutrons. And you have to understand that protons are positively charged particles. So they are positively charged particles. Electrons are negatively charged particles. So they are negatively charged particles. Neutrons are uncharged. Notice the word says neutrons from the word neutral. So they are uncharged. You have to understand that. Uncharged. Okay, so these are the three parts of an atom. Atoms are made up of protons, electrons, and neutrons. I hope you understand that. Now, when you look at an atom, you realize that protons and neutrons are in what we call the nucleus of an atom. So inside the nucleus, you have protons and neutrons. So when you're describing an atom, understand that the atom is made up of a nucleus. This nucleus contains these first two parts or particles of an atom. Protons and neutrons are inside the nucleus of an atom. Now remember that protons are positively charged particles. Neutrons are neutral. Then outside the nucleus, which is within the shells, you have electrons. So let's write here. Don't have much space here, so you can understand. So outside the nucleus, what do you have? Electrons. Now, specifically, these electrons are not just anyhow. For protons and neutrons, they are just inside the nucleus of an atom. Electrons, when we say they are outside the nucleus, they are actually within what we call the shells. So they are actually orbiting along the shells. Now, let me draw a diagram for you to understand this. So we are going to say an atom will have what we call the nucleus. So this nucleus is going to have protons. We're going to use P to symbolize the protons. And then neutrons, we're going to use N. So that is the nucleus. Then this atom is going to have shells. These are called the energy levels. So it is going to have rings like this. These are called the shells. Then what you're going to observe is that the electrons are going to be within these shells. So you're going to have an electron there and an electron there. Then you can also have electrons in this shell also. So we're going to say we have electrons and we have electrons and we have electrons. Okay, now remember that these electrons are negatively charged. Protons are positively charged. Neutrons are uncharged. So make sure you understand this. Now, the next point that we have to understand here, this is the structure of an atom. This is the general structure. Because in an exam, you might be asked to draw the structure of, and then they give you the name of an atom. First of all, you have to think that an atom contains three particles: protons, which are positively charged, neutrons, which are uncharged, and electrons, which are negatively charged. The next thing that you need to think of, protons and neutrons are inside the nucleus of an atom. So we can say this is the nucleus. So we'll say this is the nucleus. And then these are the shells. These are the shells. So that is something that you need to think of. And then you think about the electrons. What about the electrons? Oh, these are negatively charged particles, and they are found outside the nucleus within the shells of an atom. And those are the shells, the green rings. Those are the shells. So that's another thing that you need to understand. Whenever you're asked to draw the structure of an atom, those are the thoughts that should come into your mind. Now, the other important point that you have to understand here is, we say that an atom is, let me delete this. We say that an atom is electrically neutral. Let me write this. Electrically neutral. You might be asked, what does it mean by an atom is electrically neutral? I want you to pay attention to this. The reason why an atom is considered to be electrically neutral is because the number of protons and the number of electrons is actually equal. Pay attention to this statement. When you're talking about an atom, the number of protons in the atom is equal to the number of electrons, not neutrons. Forget about neutrons. Neutrons are just there. When you're talking about protons, which are positively charged, and electrons that are negatively charged, these two are equal in number. So if you have an atom that has 12 protons, just know that when you are asked about how many electrons does it have, the same number, which is 12. That is very important when you are talking about the particulate nature of matter and atomic structure. The number of protons is equal to the number of electrons. Now, what does that do? So what if the number of protons is equal to the number of electrons? Well, what happens is that, since that is the case, remember that protons are positively charged. So let's say these are protons, positively charged. Electrons, negatively charged. So there is a law, there is a principle here which states that positive charges can cancel negative charges. In other words, when you have the positive charge that is coming from this side, so let's say it's coming from this side, and the negative charge is coming from the other side, when they come together, they cancel each other. In other words, if you have one positively charged particle, so let's say this is a positively charged particle, and then a negatively charged particle that is coming from this direction, when they come together, they are put together, they cancel each other, and the net charge becomes 0. So if you have a positively charged particle and a negatively charged particle in an atom, then they are going to cancel each other, because that's the principle. They are going to cancel each other, and the net charge, because they have cancelled each other, is going to be 0. Okay, so going back to the principle that the number of protons and the number of electrons in an atom is actually equal, then that means that if you have an atom, let's say this is oxygen, Do you know the mass number of oxygen? We are going to discuss what mass number is, but the mass number of oxygen is actually 16. So we're going to write 16 here, and the atomic number is actually 8. Now, I want you to understand that when you are talking about the atomic number, you might find something that is written like this. You have a number on top and the number at the bottom. The number on top is actually called the mass number. So that is called the mass number. And the number at the bottom is actually called the atomic number. Now, what it means is the atomic number is the number of protons in an atom. So when you are looking at an atom, you calculate the number of protons. That is the atomic number. That is your atomic number. So for example, since this is oxygen here, and we have 8 here, it shows that the number of protons inside an atom of oxygen is actually 8, because that's the atomic number. The atomic number is also called the proton number, because we are just talking about the number of protons inside the nucleus of an atom. So that is the proton number or the atomic number. It is at the bottom. Now, when you're talking about the mass number, it is the number of protons plus neutrons. P plus N, when you combine them together, the number of protons and the number of neutrons inside the nucleus of an atom. Because remember that protons and neutrons are inside the nucleus. So because they are inside the nucleus, when you find the number of protons and then you add them with the number of neutrons, the sum that you're going to have is actually called the mass number of that particular atom. So this means that any atom has got the mass number, which is the number of protons plus the number of neutrons, and it also has the atomic number, which is essentially the number of protons. I hope you're getting the point. So we'll have some questions where we'll deal with how to calculate the mass number and the atomic number. But the point here is, let's take oxygen with its atomic number, which is 8. So we must have 8 here. So this is 8. That is the atomic number. And remember, atomic number is the proton number. The proton number is something that is equal to the electron number, because the number of protons should be equal to the number of electrons, which means when you're talking about the atomic number, you're talking about the number of protons, which is the same as the number of electrons. So you can know the number of electrons to know the number of protons, because the number is just the same. Now, going back to the question, why are atoms considered to be electrically neutral? The reason is, for example, this is oxygen. Just by that principle, if you're asked, what is the atomic number of oxygen? Or the atomic number is actually 8. Okay, so what about the number of electrons? Well, the number of electrons has to be 8 as well, because the number of protons, which is the atomic number, and the number of electrons has to be equal. Now, if this is the case, you have to recall that protons are positively charged, electrons are negatively charged. Going back by that same principle that the positive charges are going to cancel the negative charges, and remembering that you have the same number of positive charges, the proton number, and the same number of negative charges, then they are going to cancel each other. The first electron is going to cancel the first proton, then the second electron, the second proton, until the 8th electron is going to cancel the 8th proton. What is the net charge that you are going to have when these cancel each other? So when they cancel each other, the net charge is actually going to be 0. So the atom actually becomes uncharged, because the number of positive charges and the number of negative charges is actually equal. They cancel each other, bringing about this uncharged state of an atom. So why is it that atoms are considered to be electrically neutral? Well, because the number of protons is equal to the number of electrons. So they cancel each other to bring about this uncharged state of an atom. So I hope you get the point. Now, the other thing that we can talk about. Actually, let's just look at some more important points on this one. So if you have oxygen, remember that the atomic number is 8. So we're going to write 8 here. There is something interesting when you're writing an atom or the structure of an atom. And that is what we call knowing the electronic configuration. How many electrons should be in each shell? Because remember, an atom has got shells. You have the nucleus and then you have shells. Because you might have a different number of electrons, but you have to know which number of electrons should be put in the first shell and also in the second shell. How many electrons? It's not just about putting all the electrons in the shells anyhow. No, there should be an order. For atoms, there should be an order. So how many electrons should be put in each shell of an atom? Because remember, you know that an atom has got shells. The nucleus and then the shells. Inside the nucleus, you have the protons and the neutrons. In the shells, you have the electrons. So how many electrons should be put in each shell? I want you to remember something here. There is this formula which is 2n squared. You have to remember this formula. 2n squared. Now, when you pay attention to this particular formula, it will stick into your brain. You will not need it. You just be using your mind to know, okay, we should put this number of electrons in this particular shell. But 2n squared is very important. This n is pointing to the shell number. So how do we use this particular formula to know how many electrons should be put in each shell? And remember, for the oxygen atom, we have 8 as the atomic number or the proton number, which means that we have 8 electrons for the oxygen atom. We have to know how are we going to put these electrons in the shells. So you might have more than one shell. Some atoms might have one shell, some 2, 3, 4, and so on. The number of shells should go and increase just like that. If you want to know the number of electrons that should be put in the very first shell, remember you have the nucleus. So this is the nucleus. The first shell will be like this. How many electrons should we put in the first shell? Look at the formula here. The n is pointing to the shell number. What is the shell number here? It is the first shell. So that is 1. In other words, that means the value of n is 1 if you are trying to know the number of electrons that should be put in the first shell. So the value of n should be 1 because that's the first shell. So if the value of n is 1, then we can go ahead and calculate 2. Where there is n, we put the number of shells, which is 1 squared. Now, if you do the math here, 1 times 1 is actually 1. So we're going to have 2. Inside, we're going to have 1, right? And then 2 times 1 is going to give us 2. So that means for any atom that you are writing, the first shell should only have 2 electrons. Only 2. For it to be stable. That is for a stable atom that is electrically neutral. It should only have 2 electrons. So you can say, okay, let's write electrons here. We are going to say 2. So the first one here, the second one here. So you are drawing the atomic structure of an element or an atom. Then, if you have more electrons left, you add another shell. When you add another shell, that becomes the second shell. Okay? That becomes the second shell. So you ask yourself again, how many electrons should this one have? The second shell. Well, it means that the value of n here is actually 2. So n is equal to 2. Then you just do substitution here. 2, where there is n, you put 2 because n is 2 for the second shell. And then you're going to have squared here. So this is going to be this 2 in the brackets multiplied by itself. So it is 2 times 2, which is going to be 4. So you're going to have 2. Inside you're going to have 4 because 2 times 2 is actually 4. Then 2 multiplied by 4 is actually going to give you 8. So this means that the second shell should have the maximum of 8 electrons. So you're going to write them 2 here in that order. 2 here, 2 here, and 2 here. So you have the structure of an atom. If you want, or if you have more electrons left, then obviously you have to add another shell, right? Because there's no, for example, if you have, after putting the first 2 electrons, you have, let's say you have 9 more electrons. When you add the second shell, you can't add all those 9 electrons to the shell. No, you have to add only 8 of them because the maximum should just be 8. So if you remain with that one, then you have to add another shell. So you add another shell. Now for this shell, this is the third shell. If you do the math here, the value of n is going to be 3 because that's the third shell. So when n is equal to 3, you're going to realize that you're going to get 18 because that is going to be 3 times 3, which is 9. 9 by 2 is going to be 18. So the third shell should only contain the maximum of 18 electrons. And then you can go just like that as you add more and more and more and more shells. Now, the reason why this is important is because the first shell should have the maximum of 2 electrons and the second shell should have the maximum of 8 electrons. Then there is what we call instability when we're talking about atoms. An atom can be stable or unstable. For example, if you have an atom, this is the nucleus, and then you have just one shell, and then we have another atom here, this is the nucleus, and then we have 2 shells. I want you to pay attention. So for this first atom, you have only 1 electron in the first shell. In other words, this atom, its proton number or atomic number is 1, meaning the atomic number equals the number of electrons. So you have 1 electron. So you simply put that electron in the first shell. You don't need to have more shells because you don't have any other electrons. But then you can have this atom where you have 2 electrons in the first shell. And then in the second shell, you have, let's say, 2, 4, 6. Now, I want you to understand one thing. Both of these atoms are unstable. Why are they unstable? Because for an atom to be stable, it is either it contains the actual number of electrons in the first shell, which should be 2. If it lacks 1, where it only contains 1 electron, that means that that atom is unstable. Now, it's very important to understand the instability of atoms because it leads you to understand these types of questions on basic units of matter and also on atoms in general. So that atom is actually unstable because it lacks 1 electron. For this second one, when you look at it, notice that the first shell contains 2 electrons here. So that is okay for the first shell, right? Now, when you go to the second shell, notice that it contains 6 electrons. You have 2 here, and 2 here, and then 2 here. The fact that this does not have 8 electrons in the second shell shows that, again, it is unstable. Even though it contains 2 electrons in the first shell, the second shell is incomplete. So, because it is incomplete, that atom is actually unstable. Now, in chemistry, when you have an unstable atom, you don't have really much things to do with it. You want an atom that is more stable for you to do something with it. So in chemistry, we want to change unstable atoms into stable atoms. we'll come and talk about that when we deal with chemical bonding, because that's the role it plays. When you're talking about chemical bonding, it is because you're trying to make atoms to be stable. Now, usually when you're talking about these atoms, let's say we have oxygen. So if we draw, you might be asked to draw the atomic structure of oxygen. Remember, oxygen has 8 electrons. So all you have to do is you have to ask yourself, okay, oxygen has 8 electrons. In fact, you can check it on the periodic table. Oxygen has 8 electrons. So that means that it has 8 protons, right? Okay. So after you have discovered that, then you have to go and write the structure. You have to understand that the atom contains the nucleus. So this is the nucleus. So in the nucleus, you are going to have the number of protons. So you're going to say protons, and then notice that you have the number of electrons, which is 8, which means that the number of protons should also be 8. So you're going to write 8 protons inside the nucleus of an atom. Now, what else is contained in the nucleus? The neutrons. Now, the neutron number can also be found, because remember that when you're talking about the mass number is the combination of proton number and the number of neutrons. But on the periodic table, you have the mass number of oxygen, which is 16. If you have the mass number of oxygen, which is 16, you can know the number of neutrons by subtracting the number of protons from the mass number, because the mass number is simply the proton number, the neutron number combined. So if you have the mass number and you know the number of protons, you can actually find the number of neutrons by subtracting the number of protons from the mass number. So if this is 8, which is the atomic number, the number of protons, then 16 minus 8, we will look more on this one, so don't worry about that. 16 minus 8 is actually 8. So you still have the same number of neutrons, which is 8. When you are done with that, now you can add the shells. So you are going to have the first shell. So when you have the first shell, oxygen should have how many electrons in the first shell? Only 2. Remember that formula, 2n squared. Only 2 electrons, because the value of n there is 1. So you have 8 electrons in total. You add 2 electrons. So the first one, you're going to say, this is the first electron. This is the second electron. The question is, how many electrons are you going to remain with? After you've removed 2 of them from 8, you're going to remain with 6 electrons, right? So, and then you ask, okay, I still have 6 electrons, which means that I still need to add another shell. So let's go ahead and do that. So you add another shell. Now you ask yourself, how many electrons should this shell have? Well, you know that this should have 8 electrons. But wait a minute, you just have 6 electrons remaining. So what should you do? You simply put those electrons in that shell. So you're going to say, okay, 2 here, 2 here, 2 here, and then that is over. But you can see that, yes, this is the proper structure of oxygen, but it is still unstable because it lacks the full or complete number of electrons in the second shell, which should be 8. It only has 6. So if you are asked to write the electronic configuration of oxygen, electronic configuration is simply knowing the number of electrons which should be in which shell. So you have the number of shells. If you look at oxygen, you're going to write the electronic configuration as the first shell should contain how many electrons? 2. So you write 2, and then you separate these 2 by a comma, and then you talk about the second shell. How many electrons are in the second shell of the oxygen atom? It should have 8, but it has 6. So you write 6. And then that is the electronic configuration for oxygen. In fact, when you're trying to write the atomic structure, It is very important to begin with the electronic configuration. You have an atom, they say you have to write the atomic structure. Try to write first the electron configuration using that same formula. Okay, identify the proton number or the number of electrons. You have that. Okay, I have this number of electrons. How many electrons should be in the first shell? You use that formula. Oh, it should be 2. Automatically, you have to know that the first shell should have 2, the second 8, the third 18. So 2 automatically becomes the first number. So you write 2. And then for the second shell, just count the number of electrons that you're remaining with. If they are 8, then it is okay. That is a stable atom. But if it is less than 8, like in this case of oxygen, you just write 6 like that, and then that is all. Then you take these numbers, you just draw the atomic structure like this, and then you add those electrons according to their energy levels or according to their shells. If you have, let's try sodium. So let's say this is sodium. Sodium has the electron number of 11. If you check on the periodic table, it is 11. How do you draw the atomic structure? Before you draw, write the electronic configuration. So what is the electronic configuration for sodium? You have 11. How many electrons should be in the first shell? 2. That is automatic. Okay, so this is 2. Then you remain with 9 because you subtract 2. So you remain with 9. Okay, so I have 9. How many electrons should be in the second shell? There should be 8. And I have 9 here remaining. So I can put 8 of those in the second shell. And then I'm going to remain with 1 electron. So which means I have to add 1 more shell. And then in that shell, how many more electrons do I have for this particular atom, which is sodium? 1. So I put 1. And that is the electron configuration, which means if you draw the atomic structure of sodium, you are going to write the proton number and the neutron number. But you are going to have the first shell containing 2 electrons. So you're going to write 2 electrons. And then you're going to have the second shell containing 8 electrons. So you're going to write 2 here, 2 here, 2 here, 2 here. And then since you are remaining with 1 more, then you have to add another shell. So it is going to have 3 shells. And you just put that electron alone in that shell. That is the atomic structure of oxygen. So you can try more for the electron configuration before we talk about ions so that we deal with this question. Magnesium. Magnesium is Mg and its atomic number is actually 12. So what's the electron configuration? The first shell, 2. The second, remember that you are remaining with 10 after you've removed 2 electrons. So you're going to write 8 because that's the second shell, which means that you still have 2 more electrons that remain. You put them in the other shell, which is the third shell. That is how you write the electronic configuration of atoms. Make sure you understand the atomic number or the number of electrons because that is key. That is going to help you to know the number of shells that you are going to have and also the way you are going to write that. For hydrogen, as already pointed out, just want to make sure that I emphasize this. Hydrogen has the atomic number of 1. So it just has 1 electron. So which means the electron configuration is actually simple. It is simply 1. You're not going to put 2 because you don't have 2 electrons. You just have 1 electron. So that 1 electron should be in the first shell. And again, it just shows that this atom is again unstable because it should at least have 2 electrons. But hydrogen doesn't have 2 electrons. Now, having talked about the stability of these atoms, I want to give you this example. Let's go back to sodium. This is sodium. The electron configuration, since it has 11 electrons, is going to be 2, 8, 1. Now, I want to ask you something here. We want to make this sodium stable. There are 2 ways we can use to actually make this sodium stable. The first way is either we try to find 7 more electrons to add on this one so that it becomes 8. Because keep in mind, even for the third shell, though it should have like the maximum of 18 electrons, if you can go up to 8 electrons even in the third shell, the atom is still stable, because the stability of an atom lies between the numbers like 2, 8, 18. So if an atom contains 2 electrons only, it is stable. If it contains 8 electrons in the outermost shell only, it is still stable. So in this case, for sodium, you have 1 electron in the outermost shell, the last shell, that is the outermost shell. It's either you look for 7 more electrons so that this 1 is added to 7 to make 8, that is going to work. Or the other alternative is you simply remove this 1. If you remove that 1 electron, you're going to remain with something like, so this is sodium, it is going to be 2, 8. That is also stable. So the question is, which one is more convenient? Looking for 7 more electrons so that you have 8, or simply removing that 1 electron? Well, in chemistry, it is more convenient to simply remove that 1 electron. It is not going to require more energy for you to start looking for 7 more electrons. Instead, you can just lose this particular electron. So that is what is going to happen there. Sodium is going to lose an electron. Now, let's assume that it has lost an electron. So after it has lost an electron, the electron configuration is going to become like this. Now, what we have is a stable sodium atom. But something has changed here. What has changed? What do you think? So we have a stable atom because we have removed that particular electron. Now we are going to know where does that particular electron go when we start talking about chemical bonding. But there's an important point which I want you to understand. When you have a situation like this, you know what happens is, when you look at the number of protons in the nucleus of this sodium atom at this time, remember that initially the number of protons should be equal to the number of electrons. So the proton number, or the number of protons, should actually be, initially before the electron was lost, you know that the proton number was 11, right? So obviously it should be 11. And also initially the number of electrons was equal to the number of protons. It was 11. But after losing that electron, then obviously the number of electrons reduces to 10, because you have 10 here now, because 1 has been lost. So you're going to have 10. Now, I want you to pay attention. These are positively charged particles. These are negatively charged particles. That's the difference. Initially, before losing an electron, remember that this atom was electrically neutral, because the number of protons was equal to the number of electrons. So because two opposite charges cancel each other, the 10 electrons were able to cancel the 10 protons to make the net charge of an atom 0. But since now the electron number has been reduced to 10, something has changed. So what has changed? Well, notice that in this case you have 10 negatively charged particles, which are electrons, and you have 11 positively charged particles, which are protons. So what is going to happen when you use the principle to cancel the charges? You're going to see that these 10 electrons, which are negatively charged, are going to cancel with 10 of the 11 protons, which are positively charged. So in other words, you're going to remain with one proton here, one positively charged particle. Why? Because 10 of them from these 11 are able to cancel with these 10 electrons. So when they cancel like that, you remain with one electron, one proton. This one proton remains because its partner, which should cancel each, which should cancel it, was actually lost. So you lost that electron which was able to cancel this particular proton. So because that partner doesn't exist anymore, it has been lost. So you remain with one proton. Now, when you remain with one proton, then the atom is not neutral. It is no longer electrically neutral. Why? Because it is then positively charged. You remain with one charge. The 10 electrons were able to cancel with the 10 protons. And then this one charge is able to define the charge of an atom. So this sodium changes from sodium atom to an ion. An ion is going to be written like with a plus on top. That plus on top is symbolizing or showing that one electron was lost, and therefore one proton, a positively charged particle, was maintained, it remained, and therefore it defines the charge of this particular atom. So sodium is no longer an atom at this point. When it loses an electron, it becomes an ion. So keep in mind, when you're talking about ion, like in this case, this basic unit of matter, ions, just know that ions are different from atoms. How? Ions, it is either they have lost some electrons or gained some electrons. Gained some electrons in which way? Let me give you this example. So we're going to give an example of chlorine. So this is chlorine. Now chlorine has the mass number or the atomic number of 17. So if you check on the periodic table, you see that it has the atomic number of 17. I think by now you can write the electron configuration. The first shell, 2 electrons, which means that you remain with 15 here. The second shell should have 8 electrons. Then you remain with 7 electrons. So those 7 electrons should be put in the third shell. That is going to be your electron configuration. Now, notice that it is still unstable, because instead of having at least 8 electrons in the outermost shell, the last shell here is the outermost shell, it has 7. So what should happen? We ask the same question. Which one is more convenient? Looking for one more electron, or losing all these 7 electrons so that it remains with 8 electrons in the outermost shell? Well, in this case, it is more convenient for this case. It is more convenient to just look for one more electron. You add it to 7 to become 8 instead of losing all these electrons. It would take some time and strength for you to remove all these electrons. It is much easier to just look for one more electron. In the case of sodium, it is different because sodium is like 2, 8, 1. In this case, looking for 7 more electrons is more difficult than simply removing this electron. For chlorine, looking for one more electron is much easier than losing the 7 more electrons. The point is, usually when you have an atom and you know that it has 1 to 3 electrons in its outermost shell, 1 to 3 electrons, maybe it's 1 or 2 or 3, just know that it is going to lose the electrons, because up to 3 it will be more inconvenient to look for 5 more to get to 8, which should be the maximum in the second shell or even in the third shell. But if you have electrons where you have 5 to 7, these should accept electrons. They don't try to lose these electrons. They should look for electrons. For 1 to 3, they should lose these electrons. For 5 to 7, they should accept electrons. They should just look for more electrons to get to 8, because it is much easier. And usually what we are going to discover is that these are usually metals. These are non-metals. So metals lose electrons. Non-metals accept electrons. Now we'll look more on that. So in the case of chlorine, when you look at it again, it is 2, 8, 7. So when you add one electron, when it accepts one electron, this is going to change obviously. So it is going to be 2, 8, and then this is not going to be 7 anymore. It is going to be 8 because you have added one electron. It has accepted an electron. In this case, chlorine again is stable, but something has changed because it has accepted one more electron. So what happens to its atomic number and the number of electrons? Initially, before accepting this electron, the proton number of chlorine, remember that it was 17, which means that initially the number of electrons was also 17. But in this case, because it has accepted one electron, then the number of electrons has changed from 17 to 18 because you have one more. So you're going to have 18 electrons. Again, remember that these are negatively charged, these are positively charged. So because for an atom, initially this chlorine atom was electrically neutral because the number of protons was 17, the number of electrons was 17, they were able to cancel each other. But in this case, because you have 18 electrons and 17 protons, what is going to happen is these positively charged protons are going to cancel 17 of the negatively charged electrons. But when you cancel 17 of the negatively charged electrons, you're going to remain with one more electron. So you're going to have one more electron here. So because you have one more electron there, this chlorine is no longer uncharged. It is charged. This negatively charged particle, which remains, is going to define the charge of electron or of chlorine. So chlorine is going to change from being an atom to being an ion. And because it accepted one electron, you write it with a negative. If you juxtapose the two, this is sodium, which is positive. So we're going to say sodium changed to sodium ion. You have chlorine ion and sodium ion. So you have positive ion and negative ion. The reason why this is important, I want you to understand how ions are formed, positive ions and negative ions. Positive ions are formed usually among metals because sodium is a metal when they lose electrons. Negative charged ions are formed when non-metals like chlorine accept or gain electrons. So one is gaining, one is losing. So one is forming a positive ion, the other one is forming a negative ion. So make sure you understand that. If lastly, let's talk about oxygen on this one. For oxygen, if you remember again, let's use these same examples. Oxygen is 2, 6. This is stable, but it is uncharged because the number of protons is equal to the number of electrons. What should happen? Well, I said that between 5 and 7 elements should actually accept electrons. So it would be much convenient to add 2 more electrons to this oxygen so that it becomes 8 in the outermost shell rather than losing the 6 electrons. So this means that when oxygen accepts 2 electrons, it is going to become 2, 8. Now, something has changed again. The proton number initially was 8. And the electron number was initially 8. But because it has accepted 2 more electrons, it has changed to 10. Right? This is 2 plus 8. So that is 10. Then remember again that these are positively charged particles, these are negatively charged particles. So the 8 positively charged particles are going to cancel 8 of the 10 negatively charged particles. So you're going to remain with 2 negatively charged particles here. And this oxygen atom then is going to become an ion. The difference is it is going to become an ion by accepting 2 electrons. For chlorine, it became an ion by accepting 1 electron. So when you're writing this, oxygen is changing to an oxygen ion. You have to indicate a 2 there with the sign which is negative. Negative means that it is accepting electrons. So it is a 2 because it accepted 2 electrons. For chlorine, you just put the negative there on top because it accepted one electron. So make sure you understand this. This is very, 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 very important. When you come to talk about chemical bonding, you understand it so quickly. So atoms are like that. They are particles, the smallest particles of an element that can take part in a chemical reaction. When you're talking about molecules, it is two or more atoms which are combined chemically. When two or more atoms are combined chemically, you form a molecule. Let me give you an example. Hydrogen is an atom. This hydrogen is an atom, and it is also an element. When two of these combine chemically, you're going to have a molecule. And a molecule is going to be written like this. So you have H2. So that H2 is showing that this is a molecule. It is two or more atoms which are chemically combined. So you form a molecule. The same is true for oxygen. Oxygen can combine with oxygen to form a molecule which is O2. Or you can say hydrogen can also react with oxygen to give you water. This is also a molecule because two elements or atoms are chemically combined. So just know when you're talking about molecules, that's why we talk about diatomic molecules most of the times, because it is two or more atoms chemically combined. But you can have something like CH. This is also a molecule because two or more atoms are chemically combined. But for the most part, we talk about diatomic molecules, meaning you have two. Di means two, so it's two, H2, O2, or chlorine 2, and so on. So that's what you want to know on this one. So let's go back to the question that we have here. So the question is saying, which of the following substances, or which of the following shows the correct basic unit of matter contained in the stated substances? So what do you think is the correct answer to this particular one? So we have to analyze this to make sure that we get the concept of what is happening. So the first one, let's check answer choice A. You have boron. So what is this boron? It says boron, its basic unit of matter is ions. So is that true or false? Is boron an ion? Now, boron is an element on the periodic table. This boron, the fact that it is an element shows that it is an element, it is not an ion. I mean, just think about that. An ion is something that has lost or gained electrons. This boron is an element. It hasn't lost or gained any electrons, so it can't be ions. So you can eliminate that answer. If it said something like maybe boron lost an electron or something like that, yes, you can say this is an ion because it lost an electron. But in this case, it is just boron, so it can't be composed of ions. Ions are only formed if it loses or gains electrons. So that's the first thing. We can cancel that one. Mercury, what can you say about this? Is it molecules or something like that? Here, what is going to happen is you are talking about molecules. Remember, molecules are formed when two or more atoms are chemically combined. And this is formed for the most part between nonmetals, because when you talk about metals like sodium, there is nothing like sodium 2, unless you are talking about when it is existing as an ion in a compound. But when it is existing the way it is, sodium as a metal is not a molecule. Molecules will be hydrogen, a nonmetal, or oxygen, which is a nonmetal, or chlorine, which is also a nonmetal. Those are molecules. The interesting part here is that this mercury is a metal. Mercury is a metal. So it can't be molecules. It should be an atom. Mercury should be an atom or an element. It can't be a molecule or made up of molecules as the basic units of matter. So, just a minute. Okay. Yeah, so we can eliminate that one. Now, answer choice C, methane. Now, methane is written as CH4. This is methane. When you look at the combination here, it is carbon and hydrogen. So this is a molecule if you look at it, because it is two or more atoms chemically combined. So they combine to form CH4. This is not an atom. An atom is a smallest particle of an element. It can't have two different things at the same time. This is a compound or a molecule because you have two different atoms that are chemically combined. So that is a molecule. That's the definition of a molecule. Two or more different atoms that are chemically combined, you have a molecule. So you can also eliminate this one because it says that methane is for atoms or corresponding with atoms, which cannot be the case. So the only alternative here is answer choice D. Now, answer choice D is the correct one. The reason is when you look at neon, this neon is written as Ne. The electronic configuration is actually 2,8 because this is a noble gas. We'll look at the periodic table, the groups on the periodic table. So this is a noble gas, and when you look at it, this is an atom. That's how we define an atom. It is the smallest particle of an element which can take part in a chemical reaction. If at all you have to add or subtract elements or electrons from this one, it's going to become an ion. But for this one, it is not even easy. It is impossible for this one to react because it has 8 electrons in the outermost shell. When you have 8 electrons like that, what are you going to do? Are you going to add or subtract electrons? No, because it is already stable. So when it is stable like that, it doesn't need to lose or accept electrons. So that is what is going to happen. So because this is an atom, that is the answer choice that you're going to go for. So keep in mind with those points which we've discussed, because even later on, I think I'm going to give you some questions to go through, especially when it comes to the atomic structure and how to write the electronic configuration and all those things. So that's how we can answer this particular question. Neon is the best answer here that we can go for because it composes of, or it is composed of atoms. It is a basic unit. So let's look at also the third question. Now the third question says the following diagrams show volumetric apparatus. Which apparatus measures only approximate volumes of liquid? I think the key here is approximate. So approximate doesn't equal accuracy, because sometimes you can measure the volume accurately or just an approximation, like in this case. In this case, they are looking for the apparatus that you can use to measure just the approximate volume of a liquid. So which one is going to be the correct answer? Now, when you look at these apparatus, the first one here is, this is a burette. This is called a burette. And when you look at the second one, this is a cylinder. It is a measuring cylinder. Then this one, which is at point C, this is called the pipette or the pipette. So that's depending on how you're pronouncing it, but it is a pipette, a volumetric pipette. So it is going to be this, and then this one is a volumetric flask. So volumetric flask. So you have 4 different types of apparatus. Now, what you need to understand is there are only 3 among these that are able to measure the volume accurately, not approximately. Approximation doesn't equal accuracy. When we say approximately, the key point that you have to understand here when it comes to, because these are the units of measurements, the experimental techniques in chemistry, I want you to look at these 2 numbers. So let's say we have 25 cubic centimeters, since this is volume, and then we have 25.001 cubic centimeters. So you have 2 numbers there. What you realize is that the measuring cylinder, if you've checked it, it is like in millimeters, and then you have centimeters. So 10 millimeters makes up 1 centimeter. You will never find any measuring cylinder that is able to measure accurately something like this, 25 point, and then you have some values. But it can measure, for example, 25 cubic centimeters. It can measure 10 cubic centimeters, or 11 cubic centimeters, or 12 cubic centimeters. A measuring cylinder can do that. But when it comes to some minor details where you have points like 25.0001 or 25.0005, a measuring cylinder cannot accurately measure that one, because it doesn't have in its apparatus, there is no indication that it can measure accurately these points. It can only measure these whole numbers for the most part, 25, or maybe some even numbers, 7 centimeters, cubic centimeters, 8 cubic centimeters, or 30 cubic centimeters. When it comes to either 7.0005, it can't. So when you compare the two, for example, in this case, 25 cubic centimeters and 25.001 cubic centimeters, the difference is you can use a burette to measure this. A burette can measure this. A pipette can also measure this. Even this volumetric flask can also measure this. The only apparatus that cannot measure accurately, this one, is the measuring cylinder. So it can only measure approximately. So for example, you are trying to find the volume of this 25.001 cubic centimeters, and then you just have the measuring cylinder. It means that you're not going to get this accurately, but you can measure 25 as an approximate, very close to the value that you are looking for. That is the measuring cylinder. So that's basically what you need to know, because these are also key facilities that we use in chemistry when we are trying to measure some volumes or something like that, especially the burette and the pipette. When it comes to titration, you usually use these because they are able to measure accurately. So when you're talking about analytical chemistry, you're trying to measure accurately. These are some of the apparatus that we use, that like the burette, the pipette, and the volumetric flask. Sometimes even the measuring cylinder, but the difference is that this measuring cylinder cannot accurately measure the volume that you're looking for. So I think basically that's what we can say on that one. So we still have some minutes. We can we can still look at some more questions. So let's look at question 4 here. So question 4 says, Which mixture can be separated into its components by adding water, stirring, and filtering? Which mixture can be separated into its components? So this is an act of separating something. By adding water, you just add water and then you stir and filter. What would you say? Now, I don't think this is a difficult question. All you have to do is just understand what is being given here, because you want to separate. That's the first thing. So this is a separation technique, and then you want to separate into the components. Which method are you using? Simply adding water, and then you stir, and then you filter. So just from this question, you can see that the reason why you're adding water is to make sure that, because you're trying to separate two components, one has to dissolve after you've stirred. After stirring, one has to dissolve in water, and then the one which is insoluble is actually going to remain, and then you can filter. That process is actually called filtration. That's how we filter things. And when we are talking about separation techniques, you have like filtration, where you filter something. For the most part, it depends on solubility. A substance that is able to dissolve, because you have what we call a solvent. What is a solvent? A solvent is a liquid into which a solute can dissolve. So we have a solute. A solute can dissolve in a solvent to produce what we call a solution. So an example of this would be water is a solvent. In fact, water is a universal solvent. Many things can actually dissolve in water. That's why water is very, very important. The solid is going to be salt. So let's go and take salt as an example. So you have salt. So this is salt. And what should happen? You get a beaker or any bottle, you put water in it, and then you put this salt, which is a solid, into that particular solvent. You see that it is going to dissolve, especially if you stir the upcoming solution. So when you stir that, it is going to dissolve. You're going to have what we call a salt solution. So it is going to become a salt solution. So keep in mind, these three things are important as well. A solvent is a liquid into which this solute, like a salt, is going to dissolve. And then this solute is simply a solid substance which is able to dissolve in that solvent. The combination of the solid and the solvent is what we call a solution. So you can have sugar solution. This is another type. Sugar solution, salt solution, or anything that you can dissolve in water, it can form a solution. But you have three things. I want you to make sure that you understand that. So with that in mind, this is filtration. You can't possibly answer this question unless you understand which one is soluble among the options given. Because you might understand what the question is talking about, but if you don't know which one is soluble and which one is not soluble, it will be difficult for you to simply understand the answers, the correct answers. So let's analyze the answers here. So we're going to get option A, for example. We have iron. Now, iron is a metal. So obviously, you know that iron is not going to dissolve in water. I've never seen any metal that dissolved in water. So in that case, it is going to be a residue. After filtration, it is going to be filtered out. What about sodium chloride? Well, sodium chloride in chemistry, this is the chemical term, but sodium chloride is actually table salt. The same salt we use is actually called sodium chloride. So is that able to dissolve or not? Of course. So obviously this seems to be the correct answer, because iron is not going to dissolve, sodium chloride is going to dissolve, and then when it dissolves after stirring, because remember that you're adding water and then you stir and then you filter. When you add water and stir, this sodium chloride is going to dissolve in water to form a solution. But the particles of iron are going to remain. So when you put that on the filter paper, if this is the filter paper, you're going to see that if you put a solution there, with some iron particles, you see that what you're going to have after some time is this beaker containing this solution, which is going to pass through that filter paper, and then on this filter paper you're going to remain with the solid particles of iron. So they are going to remain there. That is how we are going to separate that. That's how we use filtration to separate the two. But keep in mind, the fact that iron cannot dissolve in water shows that it is the insoluble particle of that mixture. Sodium chloride, which is table salt, can dissolve in water. When you pour that entire solution on the filter paper, only that solution is going to pass through, and then you're going to remain with the particles of iron. Hence, you've separated the two. When you look at option B, notice that you have iron, which is insoluble, but even sulfur is insoluble. Sulfur cannot dissolve in water. Sulfur can only react with oxygen for the most part, especially if you're trying to form sulfur dioxide and sulfuric acid. Sulfur cannot dissolve in water. When it comes to option C, what is happening with option C? Now we'll look at, because these are salts, potassium carbonate and calcium nitrate are salts. We'll look at some parts of the acid, bases, and salts. All carbonates, especially potassium carbonate, are actually soluble in water. Potassium carbonate can dissolve, and calcium nitrate also can dissolve, because all salts that are nitrates are soluble. We'll look at that. And potassium carbonate is also soluble. So imagine you add water, you stir, it means that all these two are going to dissolve. So what are you going to filter out? Nothing. So you're not going to accomplish your work here. The separation is not going to take place because both of these are able to dissolve in water. And then when you look at option D, again, sodium chloride is actually soluble, but even this copper sulfate is also soluble. Copper sulfate is soluble. All sulfates, in fact, are soluble except barium sulfate and lead sulfate for the most part, but all other sulfates, they are actually soluble. So the same is true for this one. C and D, they are all going to dissolve, and you're not going to do the separation. It's not going to work out. All right, so that's our answer, and I think we'll look at some questions connected with the other separation techniques, because you have like distillation, simple distillation, fractional distillation, and then the separating funnel. In fact, for the separating funnel, I think there's a question here in the paper, so we'll look at that. But also chromatography, paper chromatography is also important. So we'll look at all those things, but for now, you can just understand answer choice A is the correct one. So let's look at question 5. I think question 5 is not difficult. Question 5 is not difficult because we've just discussed this. Notice it says an atom of an element R. So this is element R, and it has the electronic configuration of this 2, 8, 3. Now already when you have 2, 8, 3, you know that this is of course unstable. It is unstable because it has 3 electrons in the outermost shell. It should have 8. And the fact that it has 3, for it to be stable, it has to lose those 3 electrons. And if at all it loses those 3 electrons, you know that it is going to change into an ion. So R is going to become R 3+. 3 showing that it lost electrons, 3 electrons, and plus is showing that it indeed lost electrons. So this is the metal. So that's the first thing that you need to understand. The question is, which of the following statements about element R is correct? Which of the following statements about element R is actually correct? So what would you say? Let's analyze these options. Just use the same knowledge that we've we've discussed. Option A says this element R forms an ion of charge 3 negative. It says 3 negative. Is that correct or incorrect? You know, we've just explained that that cannot be the case. This is incorrect because as opposed to forming a negatively charged particle ion, this is going to form a positively charged ion because it is losing those 3 electrons. So R is going to become R3 plus, not R3 minus. That is for nonmetals that are accepting electrons, not losing electrons. So I hope you can get that one. So that is incorrect. Option B says R forms an ion with the electronic structure of neon. Now, what does that mean? Remember neon, I just wrote it. Neon has the electronic configuration of 2, 8. So, do you think it is true that this R forms an ion with the electronic structure of neon? It's not talking about it being an atom, but it forms an ion, and that ion is going to have the same electronic configuration as this. So let's go and test that. So this is R. It has 2, 8, 3. By the way, just by looking at that, you can know that it is having 13 as its atomic number, or the number of electrons, the number of protons. So it is going to lose an electron. What happens when it loses an electron? It means that the proton number is going to be 13, but the electron number is going to change because it has lost 3 electrons. So it is going to drop from 13 to 10. So after that, you have to recall again that these are positively charged ions, these are negatively charged ions. Using that same principle, these 10 negatively charged electrons are going to cancel 10 of the 13 positively charged particles. So 10 of them are going to go, and you're going to remain with 3 positively charged particles. So this is what is going to form an ion because it is going to define the charge of an atom. So R is going to become R3 plus. But if you lose 3 electrons, then it means that what you're going to remain with is R, which is 2 in the first shell and 8 in the second shell. The 3 electrons are gone, so you're going to remain with 2, 8. This is similar to the electronic structure of neon. So that is the correct answer. It should be the correct answer. So answer choice B is the correct one. When it forms an ion, that is after it has lost those 3 electrons, it is going to remain like this because this 3 is going to go, you're going to remain with 2, 8. So which means that for you to just get this answer correct, you also have to understand the electronic structure of neon. When we come to some questions on the periodic table, you have to understand that. And neon is part of the noble gases. These noble gases actually they are stable. They have 8 electrons in the outermost shell for the most part, and they don't react. But let's also test these other options. Why are they incorrect? Why are they incorrect? So let's look at answer choice C. R is a non-metal. Now, why is that incorrect? That is incorrect because it is losing electrons. 2, 8, 3. Metals lose electrons, so this one is losing electrons. It should be a metal. In fact, it should be aluminium. If you look at the numbers here on the periodic table, the fact that it is losing electrons and forming positive ions shows that this is a metal and not a non-metal. So this is an incorrect answer. And answer choice D says that this element R reacts with metals. That is also impossible because it is a metal. A metal cannot react with a metal. A metal reacts with non-metals. And because this R is a metal, it can't possibly react with its fellow metals. It has to react with non-metals. So this also is incorrect. So you can see the reason why answer choice B is the correct one, because all these other options are not actually making sense. They are not fitting the description of the metal that we've been given. So basically, these are very, very important points when it comes to chemistry. They help you understand how you can answer such questions, because I can guarantee you, when it comes to the atomic structure, you will find questions in the exam. You will have to find questions on the atomic structure. Either it will be about chemical bonding, which we'll look at, or it will be about the electron configuration, how to write the atomic structure, or how to identify an element like this. Usually they bring questions like this where you have to analyze, is it making sense? If I try to look at it, it loses electrons. Can it be a non-metal? No, because it is losing electrons. Metals lose electrons. Non-metals accept electrons. So in this case, R is clearly losing electrons, so it can't be a metal. It can't be a non-metal, but also it can't react with its fellow metals. It has to react with the non-metals for it to be okay. So I think let's look at the last question, which is question 6, and then we are good to go. So the question is, identify the diagram in which a pure element is in solid state. Now, this is also another important point. So I'll just give a summary. Next time, I think we will come and dig deep more on the states of matter and the changes of state. But you remember that matter is made up of particles, ions, molecules, and atoms. And matter exists in 3 states. So this is solid, and this is going to be liquid, and this is going to be gas. So we're going to say solid, liquid, gas. So the first thing is, when you're looking at the solid state of matter, I mean, this is how it happens, because when you're talking about matter, you're talking about something that has mass and occupies space. So it can be in solid state like ice block, it can be in liquid state like water itself, or it can be in gaseous state like water vapor or steam. So when you look at the arrangement of particles, because matter is made up of particles, so how are these particles arranged in these 3 states of matter? Well, you just have to understand this. In a solid state, particles are closely packed. Notice that they are closely packed. In liquids, they are loosely packed. In gases, they are widely packed. So you can see the difference there. A solid, liquid, and gas. Now, for the sake of this question, we are just going to look at this. Next time, we are going to discuss more on what is happening here. But just looking at the arrangement of particles, we can look at the question. But let's first define a pure element or a pure substance. What is a pure substance? In the common language, a pure substance or element is the one that does not contain impurities. If you don't have any impurities, then that is a pure substance. Not only that, it is different from a mixture, because there is nothing strange that is combined with it. Pure is pure, and it is talking about a pure element. Remember, pure element. An element should not have anything else attached to it, because it is an element. It is made up of particles which are called atoms, and these atoms are similar, just like the black people are like one race, and then all people that make up the black race are similar in color. That is an element. This is talking about a pure element, so it should not have anything else strange attached to it. But notice it says that it should be in solid state. So the fact that it should be in solid state, this is how a solid state should look like. Particles are closely packed. So you can eliminate answer choice A because particles are not closely packed. Answer choice B also can also be eliminated because they are not closely packed. You remain with answer choice C and D because particles are symbolizing or pointing to a solid state, which is being asked here. So you can eliminate the first two choices. So which one is the correct answer here? Option C or option D? Now remember that both of these are pointing to a solid state, but one is impure because we're talking about a pure element. So which one is pointing to a pure element? Well, you can easily see that this is incorrect because notice that it is combined with other elements. So the fact that it is combined with other strange elements shows that that is not a pure element. It can't be. So answer choice C is the correct answer here, because here it, number one, shows that this is a solid substance, and number two, it is a pure element because notice that all the particles that are there are similar. They are the same, white in color, whereas in D you see that they are different. An element should have the same type of an atom, not different types. D is showing different types, and so it cannot be an element. So answer choice C is the correct one for this particular question. So this is what we can talk about, I think, for today. This is chemistry, so maybe on Thursday, the next lesson is on Thursday, so probably we'll look at physics, but this is very, very important for you to understand. So it's not about, oh, in a single day we have to finish the paper. No, what is important is for you to get the concept of what is happening, because if you go through this entire paper with us the way we are doing it, and then you get the other paper, try to solve it, you see that you are able to answer most of the questions because the concepts are not very different.